Thanks for joining. This is a second experiment dedicated to the ballistic. In the first one, we assess the velocity of the bullet by means of the ballistic pendulum, and here we make a step forward and we want to develop something more to study the trajectory and to assess the results by means of the theory using two mathematical models. Eventually, we'll judge which model is more effective to describe the phenomenon. We start first with the observation and then we make the theory to justify what we have seen. I don't want to bore you with a lot of mathematical steps. They are available in the presentation, so you can easily stop the presentation to deepen over there, but my intention is to focus on the main concept to explain the assumptions, concept of the physics which are behind. Let's start with the experiment. So what we need is material, one gun, 3 bullets. We shoot with different angles in order to get the maximum range, and we know the maximum range we get for theta 45 degrees, and then we change also the shooting direction to eliminate the effect of the wind or any other disturbances. And we measure the distance of the shot, the flying time, and the maximum height. That's me. Also, this is a trajectory that we got by means of the slow motion camera, and we meter the distance up to the maximum high and the maximum high, and eventually we meter also the shooting time, which is 20 seconds divided by 8, because the slow motion is increasing the time by 8 in 2.5 seconds, and we meter also the distance of the shot by means of the same reference as above. So we count 23 panels here in the horizontal direction, which are 23 meters. So finally, 23 meter long, 8.5 meter high, 2.5 seconds the flying time. The question is, are the equations, the theoretical ballistic, enough to display our observation, to justify the values we have found? The equation is giving a parabola from which we get the range L, the height H, the maximum time, and using our values, the shot is traveling at 20 meters per second with an angle of 45 seconds. We find 41 meters of range, 10.2 high, and 2.9 seconds time of the flight. It's different. So there is a deviation which is quite significant. Also, we cannot rely on the model. We need to find a different one or to refine the existing. We will see how. Definitely, we want to change the previous equation, and we will add another term, which is the aerodynamic force for both axes. And this force is proportional to the square of the speed, and there is a coefficient in between, which is the aerodynamic coefficient, A, or alpha, proportional for the density of the air, the cross-section of the bullet, and there is a drag coefficient, which is also given by the literature. In this case, it's 0.42 dimensionless. It's depending upon the shape of the bullet. This is a number, which is a parameter, which it's a constant in our equation, but the question is not numerically solvable. We can only find a numerical way. Sorry, it's not analytically solvable. And for finding a solution, we have a trick. The trick is to express everything in function of the velocity. So instead of y double point and x double point, which is the acceleration, we replace with the derivative of the speed along y and along x axis respectively. The derivative is also, in the numerical approach, transformed into a ratio delta v over delta t. And this is the numerical expression of above equation, which are now going to solve. We make another simplification. We divided by m both members, and we introduce the coefficient gamma. It is the aerodynamic factor divided by the mass of the bullet. Differently from the ideal equation, the mass in this case is not negligible, is playing an important role. The delta v is given by the difference of the velocity at the time t plus delta t and the time t for both y and x axis. Thanks to that, we can express both equations in function of velocity y and velocity x. The first member is calculated at time t plus delta t, and the first member at the time t. So it means the first member is known, so we can solve the equation. And also we can determine the space by means of those equations below. The solution of the numerical differential equation is given step by step, starting from t equals 0 up to t equals t star, being t star the time when the bullet is touching the ground. And in this time, the x is giving the range. For the maximum high, the time is given by the condition velocity on y-axis approaching 0. We want to make the first step together. The initial conditions are t equals 0 and y and x are 0 because it's origin of our reference, and the velocities are also equal, 4.2, because the angle is 45 degrees, and we decide to have a step of 0.05 seconds. The smaller is the step, the finer is the solution, but the more is the time for solving it. Also, by replacing the values we have found, including velocity, 20 meters per second, we find for the time delta t the new values of Vy 13.3, which is less than 14.2, and 13.8, which is also less and different. And for the position, we get 0.71 for both, which is different from 0, so the space is increasing. For the following step, we need to replace y0, x0 with yx respectively, which are the ones we have found right now, and vy0, vx0 with vy, vx found right now. And so on, we get step by step to the final solution. We can display the chart and we'll see the graphic in the next slide. Those are the charts given by the two equations. The orange is the ideal case, the red the numerical one, and from which we get 7.4 meters the high and 23 meters the range over 2.5 seconds of flying time. The experiment data are quite comfortable because they are giving the same values for range and for time. There is only a deviation for the high, which is 1 meter more, but this can be due to the fact that this is the only indirect measurement and can be an effect of the perspective in the picture. So eventually we are satisfied, the model is fine, and for the future we won't neglect the air friction. It's a big difference. Thanks for joining, thanks for listening, and see you again.